Okay, hello everyone. Today's seminar will be over mathematical computer science. I think is the name of today's class. I'm Kevin Chang. I'll be your instructor today. Originally, it was supposed to be Andrew Kai, but due to unforeseen circumstances, he will be your TA for today's class. Let me know if you guys can all hear me in the chat, and I will start the class very soon. Okay, so if you do have any questions, feel free to ask Andrew. He will answer your questions to the best of his ability. And we'll get started. We'll first talk about what is mathematical computational science. So essentially, it is the math-oriented aspect of programming computers and algorithms to solve different types of problems we see in everyday life. So for example, your GPS, when you use traffic and stuff, it implements an algorithm. Like if you use Google Maps, if you use like the maps provided by Apple, all of these programs all have code in the background, which will run when you input where you are and maybe where you want to go. And then what it'll do is it'll take its data that it has on all the different routes, all the different roads, and then it'll run some algorithms and math in the background to calculate the fastest path from one position to another position. And of course, there are a lot of small tidbits you would have to go into in order to implement this correctly. It's very advanced, and it's too advanced for us to talk about today. But we'll talk about some similar, more basic algorithms that we can use when we're talking about these kind of things. But first, let's talk about how the basics of computer science works. So one fundamental structure we see in basic computer science is what is called a for loop. So a for loop, essentially what for loop encoding does is you input a certain index or some sort of identification you want, and then you'll run a certain command or a series of commands for every single index in a certain set. So for example, if I have a set of numbers or letters A, B, C, D, and E, this is a set of numbers, I can use a for loop to iterate. We say iterate usually in computer science, to iterate through every single item in the set. For example, if I want the computer to output the phrase A, B, C, D, E, I can use a for loop to go through each of the elements in the set and output letter A, B, C, D, and then E. So that's the basic behind a for loop. And there's a thing in computer science known as time complexity. So this is a pretty important subject we have in computer science, and that's because this is the study of how well different types of programs and algorithms will run on the computer. So if a program is too slow, of course, we won't have a very efficient like running of the program. It won't run efficiently, and that'll be bad for the users, bad for whoever designed the code. So one goal we have in computer science is to minimize how much time it needs to calculate or perform a certain task. So in this case, a for loop is something we say is a linear time. And that's because in this case, let's say we have 5 elements in the set. So 5 elements. And our for loop will have to iterate 5 times and perform the same operation 5 times to move through all the elements in the set. So we have 5 operations. And that's because each of our operations is we iterate and then we print out or we display whatever letter that is. So in this case, in the problem I just showed you, we have a time complexity of like a linear standard essentially, because we have 5 elements and we're doing the exact same. If we had X elements, if we had X instead of 5, we would have to have X operations. So this is a kind of a linear output. So let's talk into more about time complexity. I'm going to first teach you a bit about the basics of how we use math and time complexity and how we can calculate different types of algorithms and how fast they will run. So in time complexity, we use a type of notation known as big O notation. And there are other notations that we use, such as like regular O and small o, but these are lesser used compared to big O. And so what big O notation means is we are looking at the worst case scenario. So if we look at the worst case scenario, we're essentially analyzing what is the possible worst time that the program will complete running a certain operation. So let's go back to our previous scenario with our sets here. So let's look at our set of 5 elements. If I were to give the computer a task using a for loop to find the letter C, for instance, the for loop would iterate through each of these elements and say, let's first check element 1, that's A. Now, A is not equal to C, so let's keep moving. We're looking at B now. B is not equal to C, so we keep moving. And hey, we're at C now. So that took us 3 steps. However, let's say that we don't know exactly what the set is that we're moving through. We know it's 5 elements, but we don't know which position C is in. For all we know, C could be in the first position, like C, B, A, D, E, or it could be in the very last position. So it would be something like A, B, D, E, C. This is a possible set we can have. So if we're looking at the worst case scenario, we want to analyze a scenario where we are having the worst possible performance of our program. So our for loop in this case would not be doing 3 steps because it would go through A, B, D, E, and then finally at the 5th step, it would arrive at C. So that would take us 5 steps. So in this case, we have a set of elements and we were looking through it. We were searching for a specific element. This is known as a searching algorithm. We're essentially searching for a particular thing. In this case, using a for loop here, we have 5 steps for 5 elements. So that's, again, we have linear time complexity. So big O notation, when we have a linear time complexity, we usually say we have the time complexity of, we write a big O and then letter N. So this N means that if we have N items in our input, so items, so essentially our input is of size N. So input is size N. Then our time complexity, how many steps we need to perform in the worst case scenario, the time, the number of times slash number of steps is going to be proportional to N. So it's going to be proportional to N. Of course, there are some other factors, but N here is what we call the biggest contributor to the time. So for example, if my code, let's go down a bit. If my code were again to search for C and I had A, B, D, E, C, if it was to search for C and then output something like high, so if that's my code, I would search for C, find C in this position. That takes 5 steps, as we mentioned before. And then I would need to output high. So if you're going to output the phrase high, that takes the computer about 1 operation. So that's 1 step. So this takes a total of 6 steps, right? But if our input had been a very large number of steps, such as 100, if had 100 elements, this would take 100 steps. And then if we just add the 1 high in the end, that's just 101 steps. So it's not slower by much. So in this case, adding this 1 step has a time complexity of O of 1. And that's because no matter how many elements we had in our input, if we had N elements in our input, it would still take only 1 step to complete the execution of our program, of executing the high right here. So in this case, this part we know is O of N from earlier. If we have N elements, it will take N steps. But then for this entire scenario, what is our time complexity? Well, our time complexity should be O of N plus O of 1. And what is that going to be? Well, the trick about big O is that we don't care about smaller terms. We're looking at the worst case here. So we're looking only at the biggest contributing term in our program. So that would be the O of N. So we would just directly say that O of N plus O of 1 is just O of N. And big O notation is actually something we use in mathematics as well, and something known as asymptotics. This is a field in mathematics. And it's essentially analyzing how functions perform compared to other functions. So in this case, we can classify any function such as mx plus b. This is a regular linear line. This can be classified as O of n. Even though it's not only just this linear term right here, this is the first degree term, but there's also a constant term, but we don't care because the rate at which this grows, like how this grows is at the same speed of O of n. It's just linear speed. It's proportional to whatever n. Oh, we could use x here instead of n because we use x here. So that's essentially how this works. So let's give an example real quick. I'll give you maybe like half a minute. So the first example will be if we have a program that has 3 steps. So step 1, not 3 steps. Let me use another phrase. So 3 parts, part 1, part 2, and part 3. And part 1 has, individually when we analyze it, we know it has a speed of O of n. This is O of n squared. And then part 3 is O of 1. What is the overall speed of the program? So what is the overall time complexity in terms of big O? So I'd like to ask, please don't spam me or Andrew. It really annoys us. It annoys everyone else too because we can't answer them in return, and they'll just think, hey, why are these teachers and TAs not responding to me? Well, that's not because we don't want to respond to you. It's because sometimes you just don't see your question. So yeah, please don't spam. Take some time to think about this if you're having trouble immediately coming up with an answer, and think about what the time complexity would be. Remember, we're looking at the biggest possible term in a program. Like, what is the main contributor to the speed? And yeah, I might have moved a bit too quick through this lesson. So if you have any questions, you can ask me. I'll try to read, but ask Andrew. He's most likely available to answer any questions you may have about what we've covered so far. Okay, so I'll go over this real quick. So as before, we want to find the overall time complexity. Meaning, if the program is doing O of n, then O of n squared, and then O of just 1, the total will be O of n squared plus O of n plus O of 1. But remember, in this case, for example, the quadratic expression 3x squared plus 2x plus 1, this should just be classified as O of n squared, even though it has a linear term and a constant term, because the biggest term in the expression is the 3x squared, and that is of quadratic speed. So in this case, if we're just adding a quadratic term, a linear term, and a constant term, it doesn't matter what these two are. These don't matter because they're slower than O of n squared. So this just ends up just being simplified to O of n squared. So this is like a really cheeky way kind of to classify different types of mathematical expressions. But it does work because our main concern isn't how the slower parts will handle. If we're running very large programs where the input is huge, we don't really care about the smaller terms. For example, I'm going to relate to you how many times a computer can perform an operation per second. I think usually a computer can perform about 10 to the 9, so 1 billion operations per second. This is a pretty safe estimate. So with 1 billion operations per second, if, let's say, you wanted to run a program within 1 second, so it executes fully within 1 second and calculates and gives you an answer, but your speed is O of n squared, this can tell us how large our input is, how large our input can be, right? Because if, let's say, if we want this to be less than 1 second, and then we have an input of magnitude 10 to the 5, well, if we just square 10 to the 5, that gives 10 to the 10. So given some coefficients in front, this is definitely way more than 10 to the 9 operations. So the program won't be able to calculate the answer for this input within a second, and it would fail. So we would want to restrain what our input can be based on what the time complexity is, and also based on what time we want the program to complete within. So that's why time complexity matters in these cases. And it's also interesting to analyze time complexities of different algorithms so we can ensure that we're trying to find the most efficient process to solve a certain problem. If you have any questions, just message me right now and I'll go over any misconceptions or problems we may have with this. And then I'm going to go into an example real quick. Okay, so I believe on a new page now, I believe the first important topic I want to teach about is called optimizing your programs. So what optimizing a program means is sometimes our programs, we can finish a problem, we can solve it correctly. For example, if I were to implement some type of program to calculate the fastest route on Google, maybe what it would do is it would calculate how fast I can move on every single possible route ever, and then it would find the smallest one. And that would be a successful way to find out what's the fastest path to one area. But given how many possible roads there are, that would take way, way, way too long to compute. And so if we want to calculate something quickly enough for a user or for a certain type of problem, we want to optimize our program. We want to make sure it's running as efficiently as possible. We're not doing things that are repetitive. We're not doing things that can be simplified. And we're doing everything as perfectly as possible. That's what optimizing is all about. So in this case, let's go back to our search problem. So initially, I introduced the idea of a linear search. So what a linear search was is if I had a set of, let's use numbers this time. If I had a set of like, let's say 1, 3, 2, 5, and 6, a set of these numbers. And let's say as a programmer, I don't know the order that these numbers come in. So we get an input, we receive an input as a programmer, and we want to design code to, let's say, calculate the position of the number 5. So if we want to find where 5 is, so find where 5 is, we can use linear search because we're given the set of numbers as our input, and we just iterate using a for loop, remember? We iterate using a for loop through each of the numbers. So for example, we use the computer to analyze the first number, that's 1, and we say 1 is not equal to 5. Okay, so we know 5 is not in the first position. We look at the second position, 3, and 3 is not equal to 5. So it's not in the second position. 2 is not equal to 5, so it's not in the third position. And 5 is equal to 5. So yay, that's a success. And that means that 5 is in the fourth position here. And this is an example of using a for loop where we iterate through a set of elements to find where a certain element is, for example, 5. And so this is linear search. And this, as we mentioned before, this takes, in worst case scenario, this takes the same number of steps as the number of elements we have in this. So the time complexity should be O of n given n elements, n element set. Today's topic is mathematical computer science. So if the speed of this algorithm, the speed of linear search is O of n, then is there any way that we can make this even faster? Because remember, we're talking about optimization here. We're trying to optimize our program. Is there any way we can take less than n steps in the worst case scenario to find out where a certain element is? So I'll give you guys maybe 1 to 2 minutes to think about this. You can send me or Andrew any of your thoughts. You don't have to have any complete ideas. Just send me any thoughts you have and we'll talk about them in a bit. So yes, so we're assuming right now we just have a random input, a random order of the numbers that were given. Okay, so I've seen some pretty interesting responses sent to me, and I'll talk about some of the highlights that I think are pretty interesting to consider. So yeah, so someone pointed out, some people mentioned using maybe a backwards for loop. So let's say the worst case scenario in this case would be if 5 was at the end. So in that case, why don't we just use a backwards one? In that case, 5 is the first one. Well, you're correct in that our current worst case scenario would no longer be a worst case if we used a backwards for loop. In other words, if we started iterating from the back. But then our current best case scenario where 5 is in the very front would be a worst case scenario that we would analyze for time if we were to use a backwards for loop. And so that wouldn't work. And someone else mentioned we can look at batches at once. Maybe we can look at the first 3 elements here. So we look at the first 3 elements, then we look at the next 2, and then we say, hey, let's search through these. If 5 is in none of these, then we know that 5 is not in these. And then if we look at the next batch and we look at 5 is in any of these, hey, it is here. So we know to check inside here. And that would only take 2 steps. Well, the problem is you're correct in that it would take 2 steps to find 5 within this small batch. But in order to identify this batch, and for example, to identify that 5 is no longer in this batch, we need to first check 1, 2, 3 elements. That's 3 steps, and then move on to this batch. So in this case, that would still take a large number of steps, and it would still be O of n speed, because we're checking around approximately n number of elements for n sets, for n elements in the set. Some people mentioned using 2 for loops from both ends. Well, in that case, if 5 was in the middle, for example, 1, 3, 5, 2, 6, if we use a for loop in each end, we'd first check 1, that's 1 step. 6, that's the second step. 3, that's the third. 2, fourth, and the worst case would be 5 being right in the middle. That's the 5th step. So that's still O of n. So all of these cases, we're seeing that we can't get any faster than linear speed. And some people are starting to recommend what is known as binary search. This is another algorithm we will talk about in a moment. And this works, but only in certain scenarios. And we'll talk about that real quick. So I'll tell you now, there's no faster way given a random, unordered, so input, random, and unordered. So if we don't know anything about what we're given, there's no way to find a certain element and find what position it is in that is faster than O of n. We will never have faster than linear time. And that's because no matter what kind of strategy we're implementing, we always put, the worst case scenario will always be where the element we're trying to find is in the very last element that you're searching for. So as long as you have an algorithm which will eventually search every element in the set, you can always have a worst case scenario where the time will end up being O of n. So linear search will always have a time of O of n because we're always going to linearly somehow search for the element. But of course, some of you guys started mentioning, you might have seen these type of scenarios before. What happens if we sort it? What happens if we're using some type of median method? Well, I'll explain that in a moment. So let's say now that we know, so things we know that the set is ordered. And for simplicity, let's say it's in ascending order. So for example, that would be 1, 2, 3, 4, 5, and let's put 6 as well. So yeah. So in this case, this is an ordered set. Of course, let's say we don't actually know where 5 is because we only know it's ordered. We don't know if it's complete. Okay, let's just remove 4 purely for this example. So we don't know what exact elements there are. We know that there is a 5, so there is a 5 for now. And we want to find out where that 5 is, but we know it's ordered. So ordered meaning that it is also sorted in order. How can we approach this? Well, one strategy that some brilliant mathematician in the past discovered is to search by dividing in half each time. So we look at our set, and we don't know what the elements exactly are. We can look at the middle elements. We just, instead of searching from the beginning, let's first look at the middle one. So in this case, 3 is the middle. And we say 3. Well, okay. since our set is ordered, we know that 5 being larger than 3, is going to be above, like it's going to be behind 3. It's going to be to the right of 3. So there's no point anymore in searching these. So there's no point. Because you know that anything to the left of 3 will be smaller than 3. And 5 is larger. So we only need to search these. So this is our target now. And if there were more elements, we'd just keep using this middle strategy. We'd find the middle, determine which direction to look in, and keep repeating this process until we find where 5 is. So in this case, every time we're just dividing our set of elements, look in the middle, checking which half to search in, and then taking a look at that half, repeat the process, divide into 2 halves, check the middle one, check which half to search in, and then keep repeating this until we get our elements. And this is binary search, and that's because every time we're dividing it into 2, we're making a binary decision left or right, and we just keep doing this over and over. So let's look at what the time complexity of this is. Every time we divide n elements, so let's say we had n elements, we divide n elements by 2. And then every time we divide by 2, we add 1 to how many steps we're doing. Because this is taking 1 step, this is taking a second step, and then it'll just keep, every half takes another step. So eventually, after our first step, we're analyzing a new half set of n over 2. Take the middle of that, that's 1 more step. Now we're looking at n over 4. And we just keep doing this until we have only 1 element in the set left, and that one's going to be the one we're looking for. So for what number will n over 2 to the k, what number k will satisfy n divided by 2 to the k is less than 1. So if there's less than 1, that means there's no elements left in the set. So if we rearrange this, we get 2 to the k is greater than n. Take the log base 2, so k must be greater than log base 2 of n. So this k tells us how many times we're dividing by 2. And each time we divide by 2, remember, we're adding 1. So the time complexity is just going to be O of log base 2 of n. And if you know anything about logarithms, you'll know that there's a property where we can write this as the natural log of n over the natural log of 2. This is a constant. So this expression grows at the same speed as just the regular natural log of n. So we can just write this as O of natural log of n. And in college, in university and stuff like that, professors and mathematicians tend to write ln of n less for natural log. They just directly write O of log n. And nobody there really assumes that this is base 10, if you were confused. So yeah, this is just log base e. Base e. And so that's the speed. And so if you know anything about logs, the graph of a logarithmic graph looks something like this. And a linear graph looks like this. So as we increase, this is n, if we increase the input size, you see that a logarithmic curve grows far slower than a linear curve. And so if this is time, how many time/steps? We know that our linear search, if we just use the regular linear search on this ordered set, it'll take us much more steps to find our desired element than what binary search would do. So this is binary search, this is linear search. So in this case, binary search is much more efficient than linear search. And it's a way we can optimize our searching algorithm only if we are given the information that the set is ordered. So that brings me into my next point. What happens if the set is unordered? How can we use binary search? Well, one method we can use binary search, as many people have mentioned to me, is to first sort our unordered set. If we sort our unordered set, then we can immediately find out where an element is. Well, there are a couple of problems that arise. First of all, any sorting algorithm, I'm not going to discuss them in detail, but there are sorting algorithms available. Many types, some fast, some slow. But the fastest you will never get a sorting algorithm faster than O of n. And that's a fact that you can prove, but I'll leave that for you to search up in your own time because we have a lot of things to cover. So if you never have a sorting algorithm faster than O of n, then the speed of, so we're comparing 2 algorithms right here. So one is linear search. This is for unordered sets, ordered sets. We have a linear search, versus sorting and then using a binary search. So a linear search we know is O of n. And sorting plus binary search, let's say we don't know exactly what the O is. That's what we're trying to find out right now. But if we're sorting, we have a speed from sorting. So sorting speed we know is at least some speed larger than O of n. So let's say that this thing, the speed is just the English word speed. Speed is going to be equal to, is going to be greater than O of n plus, and then binary search, remember, takes O of log n. And then this, because n is larger than O of log n, n is, remember, n grows faster. Remember, as before, we only look at the largest possible term in our expression here. So this is just going to be O of n. So the speed will always be greater than O of n. And that means that for unordered sets, linear search will always be faster than a sorting plus binary search approach. So if you don't need to sort it for any reason, there's no point in sorting it and then using binary search, because that's just going to take longer to code and also take longer to run. It's going to be less efficient. And yeah, some of you guys mentioned that for binary search, what happens if there are odd elements on one side? For example, if we have 6 elements, what happens then? So for when we code it, we don't necessarily need to take the exact middle. We can take, for example, if we look at the 2 here, if we looked at 2 instead of 3, of course, these would be uneven sides, uneven halves. But we can use the same logic to say, hey, 5 is larger than 2. So we still need to look in these 3 elements. So when we actually implement binary search in code, you're not always going to have exact halves based on what kind of a number of elements you have. But it doesn't matter, because if we have approximate halves, we'll still be able to narrow down our search until it only takes us log n steps. So I hope that answered any questions you guys may have had. And I think that'll be it right now for searching algorithms. Next, well, we're going to talk about a different type of structure, primarily graphs. So by graphs, I don't mean the usual X versus Y plot you learn in Algebra 1 or Algebra 2. I mean more of the kind of graph structures you see when you study graph theory. So if you have any experience in counting probability, you may have encountered graph theory in the past. It's a popular topic, and the reason why it's so popular is because graph theory is incredibly applicable to real life. A lot of real life structures are all related to, can all be represented through graphs. For example, let's say you have a small town and you have roads. So let's say my school, this is my school, is right here. My house is over here. And let's say the market is right here. So maybe there are roads that connect the structures here like this. In this case, we can represent this as a system of vertices and edges. Our vertices will be each of these buildings, each of our destinations. So we can use a vertex to represent the school, a vertex to represent my house, and then a vertex to represent market. And if I want to analyze how different things can interact between these buildings, this graph structure could help me do that. Applicable, I'm not sure I understand your question. Applicable is just an English word meaning it can be applied. So graphs are very easily applied to many aspects of real life, because so many structures in our life are just representable via a vertex and then an edge, and it connects it to other vertices and other edges. So that's the idea of graph theory. So for example, I'm going to ask you a very basic, just an exercise question to make sure you're not sleeping. Is this a valid graph? There's no vertex here. So just based on common sense, do you think that this is considered a graph? Okay, so I see a couple different types of responses. I think standardly, this is not considered a graph because all your edges should be connected by 2 vertices. So an edge will always have 2 vertices at either end. If I say there's no vertex, technically there's a ending point here, but if I say there's no vertex, it means there's no vertex to that end of the edge. So that's not a valid edge, and this shouldn't be considered a valid graph. So However, graphs such as this, where there are overlapping edges, these are still valid graphs. I mean, it's still a connection between these two vertices. Although you might not be able to represent all overlaps without overlapping them, it's still considered a graph because it's a connection between two edges. So in this case, actually, if you were to draw your graph like this, and then you connect these two from the outside, there are no overlapping edges. And any graph without overlapping edges, so graph without overlapping, is known as a planar graph. So this is more relevant to the study of mathematics and some more advanced properties of graphs. But for now, we'll just be messing only with vertices and edges. So given these type of graph structures, there are some interesting questions we can answer for, including what we've previously been talking about, searches. Searches aren't only applicable to sets. We can also apply similar ideas to graphs. For example, in this graph, let's say that this is point A, B, C, D. And let's say we're told what these points are. We know we have 4 vertices, A, B, C, D, but we don't know the connections between the edges. That's something we have to get from an input. So if the computer is input a graph structure, a question might be, how can we travel from B to D? What is the fastest way we can travel from B to D, given that all edges take the same amount of time to traverse on? So in that case, we're essentially starting from B. B is our start point. B is our start. And we're searching for how we can get from B to D. So this is the idea of a search in a graph. So a graph search. And there are 2 main algorithms we use for this. There's a method known as depth first search. And this is commonly abbreviated as DFS versus breadth first search, BFS. And so the difference between these is when we're doing a depth first search, we're first starting from one vertex and we're essentially traveling in one direction as much as possible until we reach a dead end or until we find the vertex we're looking for. And if we reach a dead end, we just backtrack one move and we just keep searching our other options. So I'm going to give another graph example. Let's say that this splits up like this. And this is our start vertex. And then let's say we're looking for our end vertex right here. So how visually, how depth first search would work is that we would start from our start point. And let's say the computer initially decides to go down this vertex. So we move down here and then we say, hey, there are 2 more available options we have. Well, let's move down. Let's move down to here. And then we're here. And then we say, oh, there are no more options, no more options. And then there's a problem because we haven't reached the end vertex yet. We haven't found our desired vertex. So we backtrack one, we go back up to here. And then once we're up here, we look at our options. We've already been down this path. That means there's nothing down there. So we just go down our other path right here. And unfortunately, there's also nothing there. So we go backwards. We're back at this vertex, but we've already searched everything down here. So there's nothing here. So instead, we just go back to our start. So we know that this entire segment right here, this is a fail. Basically, there's nothing in here. So we know the computer knows to go down this path now. And essentially, we just go down the paths until we reach a dead end again. And then we backtrack. And we're here. And then say, there's nothing down here. This is a fail. Let's go on this one. And then, hey, now we found the end. So it's the idea of moving forwards until you reach a dead end and then going backwards. And so both of these algorithms don't work when there are, well, they still do work, but there's some things you can do when there are cycles. In this case, I didn't show you how we can manage cycles here. But this is the general idea. This is the same idea you'd have if you were to try to manually solve a maze. If you were given a maze, for example, a start point and an end point. And let's say the maze looked something like this. And then this. So maybe you would first decide to go down this path. Let me use another color. Let's say that you were at the start in the maze and you try to go down this path. And then you keep traveling until there's a dead end. So you know that this is not a valid path you can take. You know that this is not correct. So you go backwards all the way to your start, and then you move down this path, and you just keep trying until you reach the end. So in this case, that was a success. So you know that this is the correct path we can take. So that's the idea behind depth first search. We're searching deeply first until we find something or we find a dead end. So that's the idea. So breadth first search is the opposite. Instead of looking for everything at once, instead we look at everything around our current vertex. So let me draw the same graph here. Okay, so this is our start, this is our end. So for breadth first search, what we're going to be doing is we take our start vertex and we look at our neighbors. So in graph theory, we say a neighbor is any vertex connected to the current one, like the one you're talking about, connected to current one by an edge. So in this case, the two neighbors of the starting point would be, let's see, it would just be this vertex and this vertex. These are the two neighbors. So what our algorithm would do is we look at S and we mark it. We say we've been here before. So let's put a check mark. So we've been here before. Now we scout out our two neighbors, this point and this point, and we put them in a type of queue. And it basically just means a line. Pretend you're like lining up for McDonald's. So this is the start and end of the queue. So if we put, let's say this is vertex 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So we put vertex 2 and 3 into the queue, 2 and 3. And now we take out the first item in the queue, that's 2, and we look at 2's neighbors. So 2's neighbors are 1, 4, and 3. Well, we've already visited 1 from the check mark we see. So we just need to mark 4 and 5. So we add 4 and 5 to the queue, and then we put a check mark on 2 because we were done visiting it. Now we look at the next item in the queue, that would be 3, and we take it out of the queue. So look at 3, look at its neighbors, 1, 6, and 7. 1's already been visited, so we mark 6 and 7, and then we check mark 3, and then we add 6 and 7 to the queue. And we just keep repeating this until we move through all the vertices and their neighbors. So now we'll be going to 4. 4 has no more unmarked neighbors, so we're done visiting. 5 has no more, we're done visiting. And then 6, at 6 it has 2 neighbors, 8, 9 that are unvisited. We mark those, add them to the queue, and then we check mark 6, 7, check mark 8. We find out that its neighbors are 10 and 11, which is the endpoint. And we say, hey, boom, we found the endpoint, so found. So this is more of like a safe type of approach. If you're trying to maybe find out the entire structure of a certain graph, breadth first search would be ideal because you can find out a lot more about the graph by searching breadth first. Versus depth first search, you search deeply first, so you have a chance of being really lucky and finding it, but at the same time, you could be pretty unlucky and have to search the entire graph as well. So it should be obvious that in both worst case scenarios, we have to search the entire graph and traverse it all, like move through the entire graph in order to find our vertex. That's the worst case. So let's look at the time complexity of these two algorithms. When we're looking at time complexity here, let's look at depth first search. Let's say in this case, we had searched every single piece until we found this. We were just really unlucky maybe. And that means that we would have to have moved through every single edge. Every time we move through an edge, we mark that edge. We travel through the edge. And then every time we visit a vertex, we had to have marked the vertex. So it turns out in the end, I believe the complexity is just proportional for DFS is just going to be O of V plus E, or V is the vertices, E is the edges. And then for BFS, it's the same idea because we're looking through all of these, and then some of them we have to visit and everything, and it'll turn out to be, for BFS, turns out it'll also be O of V plus E. So in a worst case scenario, both of these will perform the same. And that makes sense because in both cases, if we had to search the entire graph for our vertex, that would be the worst case scenario. they should have around the same time complexity. So in other words, usually it comes down to preference. I believe a lot of coders, people who code, tend to prefer BFS. It's pretty easy to implement in terms of coding, and but there are always advantages for DFS as well. And one method to do DFS is with something known as recursion. And I'll bring me to my next topic soon, but we'll first talk about how this applies to DFS. So if we use a method, if we say each point can be found or not, we can say that each point can be referred to the next point when we're doing DFS. Like let's say if we know how far away, for example, if we're looking at how far away, how many edges away, how far away is the end? Well, we can use DFS and we can say there's a function, let's say f, for whatever node you're at. So in this case, we're at the starting node. Node is same as vertex. So in this case, your function would tell me how many edges away the endpoint is. And the starting node is just going to be equal to this of the two nodes next to it. So it's a recursive type of relation. And I know it might not be too clear what I mean right here, but I'll talk about recursion a bit more in detail as our next topic. And I believe that'll probably be the last topic I'll talk about for today's class. Recursion. So recursion is essentially a way of classifying states. So we classify states of a problem. And these states can be any type of condition, number, a type of function. And we use this to essentially identify at a certain point in time or point in space what a certain value is. And we're going to relate this value to other points around it. So that way, if we can calculate, if we want to calculate the point of one value, we're going to simply backtrack and calculate all the values before it to calculate that one. So a classic example is Fibonacci numbers. So in the case of Fibonacci numbers, we have the recursive relation f0 equals 1, f1 equals, f0 equals 0, I believe. f1 is equal to 1, and then any fn is equal to fn minus 1 plus fn minus 2. So this is a recursive relation because our states are going to be each Fibonacci number, and then each number has a specific index, like a specific point in space, where it is related to other points around it. So in this case, f of n is related to the previous 2 points, and it's just the sum of the previous 2 values. So if you were to compute this, you'd get 0, 1, 1, 2, 3, 5, 8, 13, and so on. And using hand, it's not too bad to compute, but let's say I wanted to ask you what f1000 was, and you had to calculate it within 2 seconds. Well, as a human, unless you memorize what the value is, it would be very difficult to do this. So we use computers to calculate these kind of larger things because computers can easily crunch through these kind of number operations at very, very quick speeds given the right algorithm. And so let's use functions here. I'm going to use functions to define the states. And functions are a type of structure usually in coding where we can implement some type of code inside of it to relate it to other things and perform calculations. So that's a bit confusing. I'll just give you an example here. Let's call the function fib of n as the nth Fibonacci number. And so this function fib of n, we can write in the function fib of n to calculate this. This is just going to be equal to fib of n minus 1 plus fib of n minus 2, unless n is equal to 0 or 1. Because if n is equal to 0 or 1, remember, we already know the value. We just output in 0 or 1. So just f0 equals 0, f1 equals 1. So this is essentially the structure you would have in programming this if you wanted to solve it recursively. Now, however, when you do this, there is a problem that arises. Let's say that I wanted to find what f of 1000 was. We'd simply just tell the computer to calculate, hey, computer, calculate fib of 1000. And the computer would start doing this method. It would say, okay, to calculate fib 1000, I will need to calculate fib of 1000 minus 1. So that's fib of 999, and then fib of 998. And then it'll say, okay, to calculate fib of 999, we apply the same formula. We just need to calculate fib of 998 plus fib of 997. And then for fib of 998, it'll say fib of 997 is needed, and then fib of 996 is needed. And it'll keep repeating this type of structure until it gets to fib of 0 or fib of 1. And in that case, it'll just know, oh, that's 0, 1, and it'll start going back, like backtracking, and it'll start calculating everything by adding them all up until we can eventually calculate fib of 1000. And although this is very easy to code, if you have any experience in coding, you should know that this is easy to code. The problem is if you directly call this value, this is very inefficient. And that's because the computer will calculate, for example here, fib of 998 twice. It'll calculate fib of 998 here, and then also calculate it here. And then 97, that's even worse. It'll calculate it once in here, and then it'll calculate it once over here as well. So this kind of process the computer takes is incredibly inefficient. And in fact, it'll take you, if you notice this is just every time you multiply by 2. So it'll take you 2 to the 1000 operations to calculate. And using logs, you can tell that this is a very large number of seconds. Number of seconds is huge. It's not even, I don't know, this is probably gonna take like days to calculate. And so yes, some people have suggested, mainly one person suggested something known as dynamic programming. That's my next topic I'll show real quick. So the idea behind dynamic programming, and I'll explain this in a moment, is instead of calculating, this is known as going from a top to bottom approach, because we start off asking the computer to calculate the top, and then it'll move each time down one step until it calculates everything at the bottom, and then it'll go to the top. So that is very inefficient. And yes, people have been pointing out very good comments in the chat. I'm pretty pleased that these are all good ideas you guys have. So instead of going from top to bottom, what happens if we went from bottom to the top? So that's the idea of dynamic programming. We're going from bottom to top. This is a very fancy way of saying, instead of calculating, telling the computer to calculate this and having it branch off, instead, we'll have the computer first calculate fib of, for example, fib of 2. Fib of 2 is easy to calculate. That's just fib of 0 plus 1, that's just 1. Now, let's calculate what fib of 3 is. That's just fib of 1 plus fib of 2. And that way, we know that that's just 2. And then fib of 4, so by calculating it in this order, we don't need to over-calculate different items. We can just calculate, for example, 4 once. All we're doing is we're just calculating fib of 3 plus fib of 2, 3. No need to branch it off. So now we just keep doing this over and over until we get to fib 1000. In this case, how many things did we take? We only took 1000 steps for this, which is insanely possible to do within 1 second of a computer's operation time. So in this case, we had to allocate this space. We had to essentially move from bottom to top, or first calculate the bottom value, and then we move to the top value. And that's how we were able to calculate this in only 1000 steps without having to repeat it in this branching pattern that the computer would naturally do. So that's the idea behind dynamic programming. And it's a common thing you would normally do in math as well. If you're given any recursive problem in math for counting probability or anything, you would naturally not start finding values and branching and everything. You would first find the base case, you find the base value and start building up from there until you get the value you're looking for. That's how we always do things in recursion. And so that's the same idea and concept used for dynamic programming. And this style of solving problems is very applicable to any type of problem where it can be solved recursively. For example, there's a very famous problem, you can search this up on your own time, known as the knapsack problem. Essentially, you're given items of different sizes or weights, and you're given a restraint as to how many how many weights you can put, and you're trying to optimize, you're trying to maximize how many items you can put in or what kind of items you can put in. So that's the type of problem. Yeah, so we have a bit of time left for today's lecture on computational mathematical science, mathematical computer science, and I guess if you have any questions, you can ask me. I don't have too much else to talk about. I can talk about a bit more about graphs if you guys are interested. There are some other algorithms that are possible, but I'm sure you guys can always search these up on your own. If you're interested in computer science, you'll definitely learn about all of these things once you start doing competitions. If you are interested in computer science and you haven't searched up much about it, there are some nice resources I would suggest. You can go to search up this. This is competition, the USA Computing Olympiad. This is a very popular competition for computer science. I believe me and Andrew, we've both done it. We're both platinum ranked in it. It's a very interesting competition. If you're interested in computer science, I'd really recommend you to check it out. There are other websites as well if you want to learn how to code. Some popular languages I believe everyone uses is you can learn in Java. Python is popular, not so much for competitions, but just in general. And for competitions, I believe also C++ is a popular language you can start learning. I don't know what the next class is. Let's see. If you're interested in these type of thinking and solving problems where you design different types of programs, this is a type of study known as algorithm design. And that's the main topic behind all of these high school coding competitions. So if you're good at designing algorithms and you want to know more about solving these type of things, I recommend to check out other websites such as, I think Codeforces is a good one. Codeforces.com probably. Anyways, there are plenty of these. You can search these all up. You guys are free to leave now, I believe. We're pretty much on the class. Thank you for coming. I'll just answer any questions you may have. It's okay. You can toss me some semi-personal questions if you want to know more about my experiences. You can ask Andrew Kai. He has a lot more experience than me actually in computer science. He's also very fluent in different coding languages and algorithms. Feel free to ask any of us a bit of questions, and I'll keep this on until probably 4 or 401. So first of all, someone asked, what languages do I know? I am mostly fluent in Java and this language known as MATLAB. It's pretty similar to Python. These two are very similar. The next subject, I'm not sure what the next subject is. I don't check the classes every day. Yeah. And I believe most of you are probably middle schoolers, if you're still on. High school does offer you computer science classes. You should sign up for those. I would recommend you, even if you don't think you're interested, computer science is a very explosive topic nowadays, especially in the future. It's going to be incredibly big in any aspect of industry. If you're familiar with coding or simply how to problem solve with coding, that'll give you a big advantage in the future. I'd really recommend you to take it in the future. If you guys are all still young, if you have many years until you enter high school, it's still not too early to learn about coding. It's only going to get more and more popular in the future. And a lot of jobs in the future will definitely all be centered around programming, designing algorithms, solving different types of things, math, and so on. So yeah, it's a great subject. When did I start learning coding? I started learning when I entered high school in 9th grade, and I got really interested in that point of time. So that's how I learned a lot about coding in a short period of time. And it's not hard. If you're interested, just put in the time, you'll be good at it. So yeah. Any more questions? If not, I'll close today's class within probably a minute. What is the slowest language? So the people who design these languages are all brilliant people. There are some languages inherently slower than others, but usually they will be slow because they have inherent advantages. One example is Java. Java runs slower than other languages because it has to compile, and it's also because of the way Java is designed. But because it is slower, it also has a lot of other advantages. So yeah. What software do I use? You're preparing for USICO. Okay, so if software-wise, when I code, I mainly code in Java for competitions. That's just what I'm most familiar in. If you want to learn Java, it's very easy. I really recommend you to learn it, even if you're not going to be coding in Java in the future. The high school AP computer science class is taught in Java, so it's definitely worth learning it. If you're going to use Java, I would recommend you to use Eclipse. It's a pretty simple way to code, run, and execute your code. You can search it up, Eclipse, have your parents look at it, help you download it maybe if you're unfamiliar with how to do that, and set it up. It's not too bad. Python could be used. Yeah, Python can definitely be used. Python is a very powerful language as well. And it's definitely a more popular language nowadays if you're going to be using computer science in college or university. So I'm an incoming college student. I just took a computer science placement test recently, and the two languages they would accept are Java and Python. So you can see pretty much how popular these languages are. It's definitely worth learning either of these. If you're going to learn any of the ones I listed here, Java, C++, or Python, they're all good languages to learn. Coding hard. Coding is not too hard. If you're going to put in the effort, just like how you learn math, it's not too much different. Just put in the effort, you'll be good, I promise. I'll probably end the class here today. Thank you for all coming. Thank you for staying for this extra short bit of Q&A in the end. If you do, okay, interesting question. I thought this is pretty funny. If you do well in USICO, can you get into Stanford? And there's no guarantees when you're applying for college. When you're applying for college, colleges don't only look at one thing you're good at. They're not going to get you into their school just because you're very, very good in one thing. Usually it has to do with either you being insanely smart in one thing, for example, like making an international competition and getting gold, or maybe you're just like very good in different aspects and they like who you are. They like what style of things you're doing. They want you to be a student in their college, and that's usually what gets you in. So there's no guarantees you do one thing, get very good, and you'll get into any college. There's no guarantees like that. It's getting more and more competitive. I'd recommend you to just do what you like to do, focus on that, and just amplify whatever you're passionate in. Website, okay, my bad. This is codeforces.com. It might not be .com. Just search up Codeforces on Google. It'll pop up. I think it's a very great way to learn algorithm design if you're interested, because it can classify different types of problems based on whatever algorithms you're using. So I'm going to end the class here. Thank you for coming. Have a good day.